What'd you say, Drake? Pretty good. Those of you who did it, not so bad, right? The half you did was good. That's a good start. With this stuff, you do have to be pretty darn accurate. They do allow a little bit of wiggle room, especially with these ones that are in the decimals, but not that much. I will say that this will pretty much every time I've seen a question like this, it's been a multiple choice question. And only one of the answers could be right. So it's not like they would give 29.6 and 29.7 as one of the answers. They'd probably give 29.6 and maybe 29.26 or maybe 29.29, one that was way farther away from that mark. So I don't think it would be as complicated as like being right on. So hopefully you're okay with converting. I want to go back a little bit and talk some more about pressure. So one thing that we did yesterday was we wrote the definition of air pressure. And hopefully you wrote these two bullets for air pressure. If you haven't already at the top of your page, these are the two bullets that go in for air pressure. Air pressure, we talked about it. My first thing I asked you was, if I just asked you about pressure, how about if I asked you to put pressure on your desk, what would you do? You'd push down. Air pressure is that, except for instead of you putting the pressure, it's the air putting the pressure down. So it's the air pushing down on either you or in this case, the desk. I did say it changes depending on temperature. How can air pushing down on a desk change if it's warmer or colder? So it changes depending on temperature. What about the molecules? What? How condensed they are. So you guys remember from the beginning of the year, and I know we talked a little bit about this yesterday, but at the beginning of the year, we talked about molecules when they're cold. What do? They condense, they get close together, or I like to call them, they cuddle. But when the molecules are cold and they condense together, are they more or less dense when they're packed in tight? They're more dense. And what do more dense things do? They get more dense, not more heavy, but more dense. And when things are more dense, I always say they sink or they're pushing down. So for air pressure, when the air is cold, those molecules are tight and huddled together. They're more dense and they sink and then push down, just like I was just pushing down on the desk. When air is cold, it's more dense and it sinks and it pushes down. So it's almost like, who can I pick on? Sorry, Remy's always a good choice. So if this is cold air, it's going to cuddle together and push down on Remy. Now, what does warm air do? Warm air, we always just say, I think we say rises usually. Warm air rises. So instead of pushing down when it's warm, what's the air going to do? It's going to rise. And how would that feel on Remy's shoulder? It would feel like there was less pressure on his shoulder. So cold air pushes down, putting pressure on Remy. Warm air rises, taking that pressure off his shoulder. So that's how pressure changes with temperature. I think I kind of glazed over that and just said it did change before. That reason that cold air and warm air rising and sinking literally controls just about everything about our weather. It's why we have clear-ish skies today, is all because warm air rises and cold air sinks. Yeah.
No,
Sam says no.
you're gonna listen to that.
Yes. No, what's your example?
So like.
Should have listened to
So
Sam.
like cold air would be like, say like a solid steel pole, and then warm air is like a big plywood sheet, and if you push it on the ground, the plywood is gonna have, it's not gonna sink as far, and it's not gonna be as much pressure in one area.
I see where you're coming from, but the key is the density though. And I don't know.
More compacted, more area.
Oh, okay. I see what you're saying. All right. Yeah. And that's less pressure. So, kind of like, if you're stepped on a toe with a stiletto heel versus stepping on your toe with a sneaker, which one's going to hurt your toe more? the stiletto because it's all concentrated on one, so there's more pressure. But not quite what I'm talking about, because I do want to talk about the sinking and the rising. So cold air sinks and pushes down, warm air rises, and it's like picking up a weight off your shoulder. All right, so that's air pressure. We did talk about a barometer. We did talk about converting back and forth. I believe we had this that's shown on a weather map with isobars. We talked about the barometer, how when air is pushing down on the barometer, it's going to go up the tube. So cold air is going to push down and the pressure is going to go up. Warm air is going to rise. So instead of pushing down and going up, when the warm air is rising, that pressure will fall. So that's how the barometer works. Then we did, this was your answers to the homework, and now we're here. So state the relationship between altitude and pressure, and we got to draw it. We talked about drawing these at the beginning of the school year. Remember, when you read them, you always read the x-axis. So as altitude increases, pressure does what? We got to talk about what happens. It decreases, you just know that? Okay, does anybody know how we know that? So what I want, it's not because air rises. Well, again, what is air pressure? Okay, so yes, and in more simple terms, it's the weight of the atmosphere pushing down. So here's the Earth's surface. Here's you with your feet on the ground. What is the atmosphere? It's the air. It's like a shell of gases that surrounds the entire Earth. I'm going to just draw it here like this. It's like a shell going around the Earth. When you're standing on the ground, how much atmosphere is pushing down on you? All of it. A lot. All of this is pushing down on you. In fact, we say that's 1 atmosphere worth of weight. Now, what does altitude mean, by the way? How high in the sky you are. So like an airplane, for example, one thing the pilot will say is, we're at a cruising altitude of blah, 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 which means how high in the sky they are. So let's say there's an airplane flying here. And yeah, guys, that's an airplane. How much atmosphere is on top of the airplane? Is it a whole atmosphere? No, look how much shorter or how much less atmosphere there is on top of the airplane. So there's truly less atmosphere on top of you when you go higher up. So that's why what Chris said was true. As altitude increases, there's less pressure. So we do need to fill this in. So as altitude increases, pressure decreases. And remember, we always put the one I can control on the x-axis. And the one we can't control, which is the pressure. And altitude's always increasing. And so you read, as altitude increases, pressure decreases. All right. Wind. So today we're going to talk about wind. Do you guys remember learning about equilibrium last year? That everything likes to be in equilibrium. Do you guys kind of remember the gist of equilibrium? It has a squiggle line, okay. What does it mean to be at equilibrium? Everybody's equal. And one thing you talked about with equilibrium last year a lot was cells with osmosis and diffusion. And one thing you learned, for example, is that the cell likes to be the same with its environment that it's in. So water or waste, for example, can go in and out of the cell in an effort to be equal. And do you guys remember which way, let's say, like waste moves? Which way does it move from the cell? From areas of blank concentration to areas of blank concentration. Do you remember which way it goes? Always goes from high concentration to low concentration. Every single time. So it likes to share, it likes everywhere to be equal. And guys, wind is exactly the same way. Wind is trying to create equilibrium on Earth. And it really starts with temperature. So let's pull this up again. Sorry, lost it. So wind, we're going to start off with wind is caused by uneven heating on Earth's surface. Areas near the equator are hotter than areas near the North Pole. There's more to it than that, but you know that for sure. Areas, so there's different temperatures. But then going back to what we said before, because there's different temperatures, we now have different pressures. So the wind is really trying to equal out the pressure. It doesn't like that there's low pressure near the equator where it's hot and high pressure near the North Pole where it's cold. So the wind is trying to even it out. And just like osmosis and diffusion, it will always go from high areas to low areas. So the wind will always blow from high pressure to low pressure. Remember, it goes from high pressure to low pressure. In the north, because it's colder, it has a higher pressure. So it's coming from the northwest in that case. There's more to it, but hold on. So just a so one thing, and this has been an example that's actually come up a lot lately in real life. The greater the pressure difference, the stronger the wind. You mean today anymore, or like time anymore? We just had some pretty strong winds this past weekend. My chicken food garbage can got blown away. The neighbor's garbage cans a couple weeks ago were across the street. Yeah, this weekend, let's talk about, so you agree it was kind of windy this weekend? Okay, Trent must have stayed inside playing video games all weekend. I knew that, sorry. So let's talk about it. Greater pressure difference equals stronger wind. We had some pretty strong winds this past weekend. So since we had strong winds, we must have had a strong pressure difference. What causes pressure again? Temperature. So really this is saying we had strong winds because we had a strong temperature or pressure difference, which was caused by a big temperature difference. Did we have big temperature differences this weekend? What was the weather at the end of last week? Do you remember? It was sunny and nice out. I don't know if we've used the word hot yet, but Chris is. So it was nice out at the end of last week. How was this weekend? It was cold. It snowed. And what's it doing out there now? It's warm. It's warm again. So we had cold weather. We had warm weather, so we would have had a low pressure. Then we had some cold weather, so we would have had a high pressure. And it was a pretty significant difference. That's why we had this strong wind. So any time that you can see like in the forecast, really warm weather followed by really cold or vice versa, you can always expect a windstorm. On a weather map, remember those isobars? Lines that connect areas of equal pressure. Well, when those lines are close together, that means there's a big difference in the pressure. It's changing really rapidly. It is also when you're going to have strong winds. Closer the isobars, the stronger the wind. So let me show you a picture of that. So you remember our connect the dots for slightly older kids and all those lines. Here's one of those maps. So it should look familiar, like we did these in chapter 2. We tended to do them with elevation in chapter 2, but now we're just connecting areas of equal pressure. So everywhere, let's say on this 1,000 line, the pressure is 1,000. Everywhere on the 1,004, the pressure is 1,004. In this general region over on the on the west side of this, you'll notice the lines are pretty close together there. That means it's going from 1,000 to 1,004 to 1,008 to 1,012 to 1,016 and 1,020 really rapidly here. Where over here, those are really spread out, going up the same amount, but over a bigger difference. It means that the pressure is changing faster here than it is over here. So you can expect a windier day for the people back here to the west than the people over here on the east of this map. The closer the lines are together, the stronger the wind. That is something you need to commit to memory. Closer the lines, the stronger the wind. And one more thing at the bottom here, and I did make this in bold, dark, large letters. Wind is always named for the direction it blows from. So when Trent was talking about those northwest winds, that means they're coming from the northwest. They name them that way so that you know what to expect. Winds coming from the north are going to be typically colder than winds coming from the south. So they kind of give you a heads up on what kind of weather to expect. We talked yesterday about different instruments used in to measure weather. Yesterday we talked about thermometers and barometers. Today we have 2 instruments used to measure wind. We have an anemometer, I think that's how you pronounce it, and a wind vane. They do 2 different things, even though they're very similar. Any idea what either one of these might do?
On the right, see those on farms.
You see these on farms. They typically have a rooster or a pig.
Probably tells you which way.
This is for telling you the wind direction. So, you have what? You're right. So you have these exact pictures in your notes. I do want you to add to them what they do. So if you want to write it at top or on the bottom, an anemometer measures wind speed. So add that. And a wind vane tells you wind direction. It's probably, I'm guessing, pointing to the way it's going. So it's pointing this way. So in this case, the wind is coming from the northeast. Yeah, so it'll point to where the wind is going. Yeah. Because they will then sometimes even act like if the wind is so strong, they'll just keep going. Yeah. All right, so that's that. Like I said, you have to memorize these. You have to memorize wind vane for wind direction, anemometer for wind speed, barometer for air pressure, thermometer for air temperature. We're gonna get a total of 5 different instruments, and you have to know what they're for. There's always a question on the Regents about one of those 5 instruments. All right, one last thing is we're going to be talking about a sea breeze and a land breeze. Besides the names, do you see any differences in the 2 pictures that you have on your paper? Chris, do you notice it? Okay, so besides the fact that I cut out half the house. Sorry, you're right, that is a difference. It's not the one I'm looking for though. One has a sun and one has a moon. Can you assume what I mean here, showing you the sun? It's daytime. Can you add that label just in case it did not occur to you? So the sun means it's daytime. And you can go down to the one that has the moon and you can do the same thing and label the one with the moon as nighttime, please. Now, there is one concept here that because I taught this out of order, we haven't talked about one really important concept. But I know it's something you know and understand. So the concept is called specific heat. Specific heat talks about how fast or slow things heat up when you add energy. In fact, let me ask you about this. When I add energy, does every substance heat up at the same rate? No. The best example I always have of this is making macaroni and cheese. The not easy mac because I need it to be on the stove. When you're making Kraft macaroni and cheese or anything that you need to boil water for, so if you're making noodles, let's say, do the pan and the water heat up at the same speed? No. And the way you know this is you can burn your hand on the pan almost right away. Can you burn your hand in the water right away? No, water takes a lot longer to heat up. Now let's talk about cool down. Do metal and water cool down at the same rate? Which one cools down faster? Who does it? Well, the metal actually cools down faster. It is hard to use my example because with the water in it, they're going to cool down at the same speed. But how about this? Let's talk about a pool and the pool deck. So you do have to picture a hot sunny day, which I know is kind of rough. It's kind of far away. Which heats up faster, your pool deck or the pool? The deck. The deck gets hot fast. Or on the same note, what about the beach, the sand, or the water? Which one heats up faster? Sand heats up fast and it gets hot. Now let's talk about the reverse of this at nighttime. What cools down faster, the sand or the water, the pool deck or the water? The sand does cool down way faster than the water. And that's because water and land have different specific heats. Means you have to add more energy to the water to heat it up than you do the land. So in this case, let's talk about it. It's during the daytime. Which one is going to be hotter, the land or the water? The land is going to be hotter. Now, because the land is hot, will it have high or low pressure? Don't shout this out. I want everybody to think it through. The land is hotter. Will it have a higher or a lower pressure? Think of what we just walked through. What does warm air do? Anybody have an answer for me? Will the land have a higher or a lower pressure? Lower. Let's walk through this for those of you who didn't see that. So we're going to start off with, oh, I guess I started with the water. So the water heats up slower than the land. Sorry, I know this is little. Can you guys add these bullets though? So I know that is kind of little. It says water heats up slower than land. And this is because, so underneath it, it's because it has a higher specific heat. So add that. That's because water has higher specific heat. We did not. Or do you mean just now? No, I don't think we talked about it. I may have brought it up on the topic you guys got me off topic about, but it's nothing that I've officially taught you yet. Because it's going to have, water's going to heat up slower, it's going to be colder than the water. So that's the third bullet, cooler temperatures. Sorry, it's going to be heater than, now it's going to be heater. It's going to be cooler than the water. I did it again. You're right. I give up. I don't give up. I'm going to try one more time. Because the water heats up slower, the water is going to be colder than the land. Said it right this time. Now, why does being colder, or so since it's colder, is it going to have higher or lower pressure? Higher. Cold air sinks. So since the air is sinking, we have a high pressure. So I added an H above the lake with an arrow saying the air is going down. Now let's do the same thing on the land side, which we already talked about. Land heats up faster than water. Why? Because it has a lower specific heat. So we're gonna have warmer temperatures over on the land. The air is rising, which gives us low pressure over on the land. So again, I added that L on the land with the air going up. Now, which way will the wind blow in this scenario? Wind always blows from high to low. So it's going to go this way. So add your wind arrow. So during the day at the beach, we're always going to have wind blowing from the water towards the land. That's why this is called a sea breeze. Now, in this case, this is a lake breeze. You can still call it a sea breeze, but it's going to be blowing from the water to the land. Now, that's a lot of information we wrote there. I would say you don't officially have to memorize this as long as you can walk through concepts. So as long as you can walk through, okay, during the day, land heats up faster. So the land heats up faster, so it's going to be warmer. Warm air rises, so we're going to have low pressure over the land. Add an L. Then you think to yourself, okay, what about the water? It heats up slower than land, so it's going to be colder. Cold air sinks, so we're going to have high pressure. Wind blows from high to low. So do you have to memorize it? You don't, but you do need to know the concepts. So we just got a couple minutes. Let's do what happens at nighttime. So at nighttime, which one did we say cools off faster, the water or the land? Land cools off. So the water is going to cool down slow. So it's going to stay warmer longer. And because it's warmer, we're going to have warm temperatures at night. Warm temperature, the air is rising, which gives us low pressure at night. Over the land, it's cooling down faster, so it's going to be colder. Cold air sinks, so we have high pressure. Wind always blows from high to low. Once you have this copied into your notes, we are done for the day. And yes, you do have homework. I'm sorry, we did not get officially time to work on it in class. It is the questions on the back of every one of the pages we've done so far. So there is homework on page 24, 26, and 28. Oops, sorry, I'll bring that back up in 1 second.